Okay, you know that feeling when you're trying to get a language model to generate something with just the right properties? You need a summary that's exactly this short, or maybe an email that sounds formal, but also, a little bit friendly. Feels like you're nudging it in the right direction with your prompt, but sometimes it just doesn't quite hit the mark right.
Absolutely. You can ask it to make it concise or be formal, and it usually gets the general idea. But achieving really precise control over specific attributes, things like the exact word count, or maybe a nuanced level of formality, or even how descriptive the text is that goes beyond just the main instruction, that's surprisingly difficult. Much harder to do reliably with standard prompting.
Yeah, it's like you have this fantastic engine for generating text, but the controls for the fine details are a bit, well, fuzzy. The current methods, which often rely on trying to describe the desired attribute in the text prompt itself, or sometimes using special discrete tokens as signals, they just have real limitations.
Yeah, they really do. As the paper we're diving into points out, natural language prompts can be incredibly brittle. You change one word and suddenly the output characteristics just shift unexpectedly, and discrete signals are essentially like on-off switches or maybe a few specific settings. They're just not built for smooth, fine-grained adjustments across a spectrum.
Right.
Plus, and this is interesting, LMs aren't naturally that good at interpreting numerical constraints like exact word counts when you just write them out in text.
Which leads us perfectly to the source for this deep dive. We've got a really interesting research paper here titled CIE, Controlling Language Model Text Generations Using Continuous Signals.
Yeah, it introduces a fundamentally different way to think about and implement this kind of precise control.
And our mission for this deep dive is to unpack this paper. We're going to explore why having this level of precise control over attributes is actually really valuable for you as a user. Look at why those existing methods kind of fall short. And then really dive into how this new approach, CIE control through interpolated embeddings, actually works. We'll then look at the specific results the researchers got, especially for something everyone can relate to, controlling the exact length of a response. Okay, let's unpack this. So to kick us off, why is this level of control something you, the listener, should actually care about? Why does it matter?
Well, think about all the places language models are used now. Drafting content for social media, right? Writing emails, generating code documentation, creating summaries for reports, filling specific fields in a database. In so many scenarios, the output doesn't just need to be factually correct or follow the basic instruction. It also needs to fit a container or match a specific style.
Yep.
A tweet has a character limit. A bullet point summary needs to be brief. A formal letter needs a certain tone. If the model can't reliably hit those targets, you end up doing a lot of manual editing yourself.
Right. And you mentioned the current approaches, natural language prompts and discrete tokens. I get why prompting for tone works okay sometimes, but what's the fundamental issue the paper highlights with these for, precise control?
The core issue is really that they're not designed for continuous variation. If you want something slightly more formal or a little bit longer or text that's maybe halfway between descriptive and concise, it's very hard to express that nuance reliably with words or simple tokens. Words like short or long are relative, they're model dependent, and discrete tokens are just, they're discrete. You can't smoothly interpolate between different tokens.
And that numerical understanding point is interesting. I've definitely asked models for exactly 100 words and gotten back, wildly different lengths. So the paper argues that trying to force a model to understand precise numbers through text prompts is inherently difficult.
Exactly. Language models are brilliant at processing and generating language patterns, sure, but numerical reasoning, especially using numbers within the text stream itself to constrain output properties, that isn't really their strong suit.
Okay, this is where the paper proposes CIE, control through interpolated embeddings. And the name gives us a hint. It's using continuous signals, and it's doing it with embeddings.
Yes, the big shift here is treating the control signal not as a command in text or a distinct token, but as a value on a continuous scale, like a dimmer switch, not an on-off button.
Yeah.
And they represent this value using embeddings. Now, if you're not neck deep in ML terms every day, embeddings are basically numerical representations vectors that capture the meaning or properties of words, phrases, or even concepts in this multidimensional space. The core idea is that similar things end up closer together in this space.
Okay, so they're using these numerical representations as the control signal. How does that work for something concrete, like controlling length?
This is where the interpolated part comes in, and it's actually quite clever. Instead of learning tokens for short or long, the model learns just two specific embedding vectors for the attribute you want to control. One represents the minimum possible value of that attribute, let's call it the low embedding, and the other represents the maximum value, the high embedding.
So for length, one embedding vector essentially means shortest possible text, and another means longest within the range they care about, I guess.
Precisely. In the context of length, yes. And for any desired value in between that minimum and maximum, say, you want a specific word count, like 150 periods, the method calculates a special control embedding. And it does this by simply interpolating linearly between the low and high embeddings.
Ah, okay.
So if 150 words is, let's say, 75% of the way up the possible range of lengths the model was trained on, the control embedding will be calculated to be 75% of the way along the straight line connecting the low and high vectors in that embedding space.
Ah, I see. It's literally like a slider or a dial.
Ah.
The position on the dial maps directly to a specific point in the embedding space, and that point represents the exact value you want. And this resulting control embedding. Where does it actually go? How does the model use it?
It's surprisingly straightforward in concept. This calculated control embedding is simply added to the input that goes into the language model specifically. It's appended to the sequence of embeddings that represent the user's text instruction.
Okay.
Then, during the fine-tuning phase, the model sees pairs of instructions and responses, and each response is tagged with its actual attribute value, like its word count. So the model learns to associate the position of that appended control embedding along the interpolated spectrum with the actual output text having that desired attribute level. It learns the mapping.
Okay, that makes sense conceptually. You're basically giving the model an explicit, continuous numerical signal right alongside the text instruction. So how do they test if this actually worked in practice?
They focus their main case study on controlling a response length, measured by word count. It's a nice, clear, objective attribute to measure performance against.
And they needed data to train and evaluate this, right? You can't just do it out of the box.
That's right. They created a data set called verbosity CTRL specifically for this purpose. It pulls from various sources, including conversational and some NLP tasks, filtered for English and typical text generation styles. The key thing was ensuring a wide range of target word counts during training, from 1 all the way up to 200 words, distributed relatively uniformly. They didn't want it biased towards just short or long answers.
Makes sense.
And they also used a specific evaluation slice called verbosity CTRL range, where they tested target lengths from 20 up 200 words in increments of 20. This was important to see how well the control held across the entire spectrum.
Testing at a range like that seems crucial to see if the dial works smoothly, not just at the ends.
Exactly. And to check if it generalized, they also evaluated it on an entirely separate, out-of-distribution dataset called Alpaca LI.
Ah, okay. Good test.
And they applied this whole method to several popular open-source models. Lamame 3.8b Instruct, Gemma 7b It, and Quen 1.57b Chat.
All right, the setup makes sense. Now for the results. How do they actually measure success? Because as we said, hitting an exact word count seems incredibly difficult.
It is, and that's where the metrics they chose are important. The strictest one is the conditioning precision ratio, or CPR. This is super simple. It's 1 if the generated text is exactly the target word count, and otherwise.
Yeah, I can imagine that number is probably pretty low most of the time.
Usually quite low, yes, for any method, because hitting an exact integer target like that is hard in text generation.
Okay, so CPR measures absolute perfection.
Yeah.
What about just being close? Because, in the real world, if I ask for 100 words and get 98 or 103, that's usually perfectly fine. That's success for me.
Exactly. And here's where it gets really interesting. They introduced CPR at K, which is a much more practical and frankly useful metric. It checks if the generated length falls within plus or minus K% of the target length. So CPR at 0.05 means the length is within 5% of the target. This really captures how useful the control is in practice. How often does it get close enough for real-world applications?
That seems like the key metric then.
It's a very informative one, yeah. They also use precise match, PM, and flexible match, FM, which were metrics borrowed from a baseline method called ruler. Ruler uses discrete tokens for length control, so this allowed for a fair comparison. PM allowed 10 words tolerance, while FM had a more variable tolerance based on the target length.
Got it. And they also checked if just forcing a length messed up the actual quality of the text, right? You don't want gibberish that's the right length.
Crucially, yes.
Yeah.
That would defeat the purpose. They didn't want models just, padding or truncating nonsensically to hit a word count. So they use win rates, employing GPT-4 as an impartial judge to compare the quality and the instruction following of texts generated by the CIE-controlled models versus the outputs from a strong prompting baseline. High win or tie rates would indicate that CIE was preserving or maybe even improving the overall generation quality while adding the length control.
So, drum roll, please. What were the results? Did CIE actually make these models significantly better at hitting those target lengths, especially at that close enough CPR at 0.05 level?
Their results were quite significant, yeah. CIE dramatically improved response length control compared to the standard prompting baseline across all the models they tested in both datasets.
How big was the improvement? Like, can you give us a sense of the numbers at that useful CPR at 0.05 level?
Sure. On the main verbosity CTRL validation set,
Yeah.
using CIE increased Llama 3 8BIT's success rate within that 5% window by over 23 percentage points.
Wow.
For Gemma 7 BIT, it was an increase of 24 points, and for Quen 1.57b, it was a massive jump, over 30 percentage points better than just using prompts.
Huge. That's the difference between getting it right maybe, a third of the time with prompting to getting it right, well over half the time, or even more with CIE, depending on the model.
Exactly. It's a substantial shift in reliability. And they also noted something interesting. Models that were initially less capable at length control via prompting, like Gemma 7 BIT in their tests, actually saw the biggest relative improvements. For Gemma, they reported over a 10 times increase in performance at the very strict exact match CPR metric. So CIE really helped models that struggled with naive prompting.
And this wasn't just overfitting to the verbosity CTRL data they trained on. Did it work on Alpaca LI too?
No, it wasn't just memorization. The improvements generalized well to the out-of-distribution Alpaca LI dataset, too. That's a strong indicator that this method isn't just learning length distributions for one dataset, but is actually learning a more robust control mechanism.
That's great. And the quality. Did the text still make sense? Was it coherent?
Yes. The win rate evaluation confirmed that. The CIE outputs were consistently judged by GPT-4 as equal to or even better than the prompt baseline in terms of overall quality and following the main instruction. So crucially, you weren't sacrificing coherence to get that length control.
That's key. Okay, and how did it compare to that other method, Ruler, the one using discrete tokens?
CIE consistently outperformed Ruler on both the precise match and flexible match metrics across the board.
Okay.
This strongly suggests that the continuous signal approach, using these interpolated embeddings, is indeed more effective for this type of fine-grained control compared to using a set of discrete length markers or tokens.
There was also that really clear visual in the paper, figure 3, showing the box plots comparing the lengths. That seemed to tell a story very simply, very visually.
It really did. What that showed was just how predictable the output length became with CIE. For the prompt baseline, as you asked for longer and longer text, the variation in the actual length you got back grew significantly. The box plots just got wider and wider.
Right, more unpredictable.
Exactly. With CIE, however, the distributions of generated lengths were dramatically tighter around the target word count, even for longer responses up to 200 words. The spread was much smaller. And importantly, the mean generated length with CIE tracked the target length almost perfectly along the diagonal line. It shows incredible calibration and control.
So, bringing this all back to you, the listener, what's the main takeaway from reading this paper? Why is this important?
I think the main takeaway is that if you need reliable, precise control over attributes like the length of the text generated by a language model, relying solely on telling it what you want in a natural language prompt or using sort of clunky discrete signals probably isn't the most effective approach anymore. This paper really demonstrates that using a continuous signal, specifically implemented through interpolated embeddings, like CIE does, provides a much more robust and accurate way to kind of dial in that control.
Yeah, it makes LMs a more predictable and therefore a more useful tool, especially when the output format and those properties matter just as much as the actual content.
Exactly. Things like fitting text into UI elements, generating summaries of a specific size, ensuring consistency in documentation. This kind of control is really valuable. And the paper is pretty optimistic that this method isn't limited to just length. They suggest it could potentially be applied to other attributes that can be thought of on some kind of scale, even if they aren't strictly numerical.
Like linguistic complexity, maybe? Or how descriptive the text is. You could imagine dialing up or down the level of detail you want.
Potentially, yes. things that are ordinal or have some kind of inherent scale, and they even muse about applying it to more subjective or ordinal concepts, provided you can define a meaningful spectrum. Things like, perhaps, levels of formality, or maybe even stylistic elements like emotional intensity. Though they do acknowledge that defining a truly continuous, measurable range for something highly subjective could be quite challenging.
Yeah, that's the really tricky part, isn't it? How do you map something like levels of politeness or, say, intensity of humor onto a smooth, learnable spectrum that a model can consistently interpret via an embedding vector?
Precisely. How do you get the training data? How do you label it reliably on a continuous scale? That's definitely a challenge for future work. But the foundation this paper lays for continuous control feels very promising. It opens up possibilities.
So to wrap up then, we've seen how CIE, by using these interpolated embedding vectors as a continuous signal, offers a significantly more precise and robust way to control attributes like response length in language model generation. It seemed to overcome some key limitations of traditional prompting and discrete signals, especially when you need that fine-grained control.
Absolutely. And the idea of having a smooth dial to adjust aspects of generation beyond just the core content is really compelling for making these models more adaptable tools. But as the paper touched upon, and as you just mentioned, defining that meaningful continuous range for more subjective attributes like politeness or sarcasm or even humor, that remains a fascinating challenge.
Which does leave us with a final thought for you to ponder. If you wanted an AI to understand how to turn the funniness dial up or down on a joke it generates, how would you even begin to quantitatively measure what more funny or less funny means in a consistent way that could actually train a model using something like CIE?
Yeah, what does that spectrum even look like?
Something to think about as you continue exploring the ever-evolving capabilities of language models.